Sure. So good afternoon, good morning, everyone. And I'm extremely sorry for the issue that we had with the link in the Zoom. So, but anyway, the lecture will be in recording mode. So first of all, I welcome our today's speaker, Dr. LUCA, who kindly accepted our invitation to be one of the speakers for today. And it was like great to have you here, Dr. LUCA. I know that you are very regularly visiting India for different projects and other things. So I feel like it's an honor for me to, host you today. And just to give an introductory, actually, these monthly lectures have been started as a cut and riser event for our conference, 12th ISFMG 2026, which will be held in IIT Indore in August 26. So as a part of the conference, we started our activities. So with this monthly activities, and from the second week of February, we are going to have some podcast also. So this is our fifth lecture of TC 220 of ISMG. So I take this as a honor to introduce our today's speaker, Dr. LUCA, who is Associate Professor at Oslo Met and Senior Researcher at Norwegian Geotechnical Institute. His scientific pursuits primarily revolve around slope stability analysis, rainfall thresholds, early warning system, risk assessment, and tailing dam stability analysis. With a portfolio of national and international research endeavors, including significant involvement in EU projects and over 20 impactful scientific papers, LUCA's expertise is highly regarded in the academic community. His contributions extend beyond research, and he convenes sessions on landslide early warning monitoring at renowned conferences like EGU and WLF. Additionally, LUCA serves as a distinguished expert advisor for START 4-1 and is a member of Executive Committee of the International Network of Land Aware. Furthermore, he is a member of the Technical Committee of Tiling and Mine Waste of the ISMG. So with this brief introduction, I welcome you again, Dr. LUCA, for this lecture series, and thank you again for accepting to be our fifth speaker. So over to you.
Thank you very much, Melima. It's actually an honor for me to present what we are doing in this series of events that you are arranging online, that kind of our preparatory event of the symposium that you're going to have in 2026. So thank you very much. And I'm going to share my screen, and I hope hope you can give me a feedback if you see it. Okay, I got the feedback from Minu, that's actually in the room. I am at NGI offices at the moment in Oslo. As Nelima was saying, I am 70% at NGI as a researcher, a senior researcher, and also I recently started a position as associate professor at the University of Oslo here, dealing with and having the course on environmental geotechniques. Today, I'm going to describe what we have recently done, this fully operational IoT-based real-time slope stability analysis that we are using as a tool for a local lens early warning. So we are going to see how we have implemented this real-time slope stability analysis in a case study. First of all, before starting, as you can see on the bottom right, you see a fruit there, a peach. Well, the point is that my surname is not that easy to pronounce, not even for Italians sometimes. So to help you understand and remember my name, I put here the peach. So the correct pronunciation of my surname is PICIULLO. So just remember the fruit, the peach, and then it's easy, PICIULLO. So after that, I think we can start. And I would start from a definition that I like about early warning systems. So we start with that, and then we build on top with all the other topics and things. This definition is general. It's about early warning systems. I like it because it's from the United Nations International Strategy for Disaster Risk Reduction. It has in it all the main keywords. words. So an early warning system can be seen as the set of capacities needed to generate and then, of course, disseminate a timely and meaningful warning with the aim of inform individuals, communities, or system managers, or in general elements that are threatened by a hazard, to prepare and to act in time to reduce the possibility of harm and loss. So we understand here that it's a group, a set of capacities with the aim of providing a warning that has to be timely to inform individuals, communities to reduce the risk, or system managers. But what's the role in the landslide risk framework? I'm using this framework from Fell et al. 2005. It's pretty famous, and early warning systems can be seen as risk mitigation options. So if we think at the formulation from VARMS, so the risk as hazard times the vulnerability times the element exposed, well, what early warning systems do, it basically they reduce the risk by reducing the element at risk. So they are non-structural risk mitigation measures. Then you may have structural risk mitigation measures that they go, for instance, they aim at reducing the risk, either reducing the hazard. For example, you do some mitigation measures in order to reduce the bow water pressure or the water table, and you are reducing the probability that an event may occur. On the other hand, you may build something, some walls or other things, or reinforce the element exposed, and in this case, you are reducing the vulnerability. Remember that the vulnerability, it ranges from 0 to 1, where 0 is no loss and 1 is complete loss. So reduction vulnerability means reduction in the risk. But early warning systems are non-structural risk mitigation measures, and the aim is to reduce the element at risk. These systems can be employed at two different scales of analysis. Slope scale, and here I refer, and I call them local LEVs, local landslide early warning systems. In this case, are all those systems addressing single landslides, where we know more or less, or we have a good understanding of where the sliding surface is. On the other hand, at a regional scale, we are dealing with systems operating over wide areas, dealing with the possible occurrence of landslides, multiple landslides, but we don't know exactly the location. We don't know exactly what is the depth or the sliding surface. And I refer to these systems as territorial landslide early warning systems. On the top, you can see some examples for local LEVs. On the bottom, you can see some example of territorial LEVs. An example is Rio de Janeiro, it's pretty famous. More famous is the one, the system operational in Hong Kong. Between slope scale and regional scale, also the instruments involved and what are kind of the variables you are monitoring for issue warnings are different. Well, another thing that I have to say is that territorial, also the word territorial, because they include systems that may be employed at a basin scale, municipality, in a province, in a region, and even in a nation. So I was saying that from the monitoring point of view, the two scales can have very different instruments and variables monitored to issue warnings. A review that me and my former colleagues have performed in 2019 were collecting 29 operational local LEVs. Well, usually these operational local systems, they don't aim to publish on journals and papers. So it may be that for sure there are more than these 29 operational online, operational worldwide. but these were the ones that were available information on internet and in literature. Among these ones, what we find out is that 28 out of 29, so the majority of them, are based on deformation monitoring. So they have thresholds, they issue warnings, mostly based on velocity rates, so on thresholds based on velocities. And this is due to the fact that most of the monitored landslides were previously recognized and they have shown evidences of active deformation. Now, a challenge arises if you want to try and we want to try to define a local labs for slopes without prior deformation. So if we want to monitor and set warnings on hydrological areas, right? And this is what this project aims at. So it aims to address this challenge, employing an IoT-based early warning systems for cases where there is not an active deformation in place, or at least it's not evident. And we are doing this monitoring and using hydrological variables. But first, I want to start by providing a definition. What is IoT? IoT stands for Internet of Things. Here I'm using the definition provided by what is nowadays, what it seems to be nowadays, the most relevant source of information. But actually, I need to say that the definitions provided were not bad, but I had to review the text. So what is an IoT in general? It's the creation of a vast network where objects can gather and share information, and then this network enables the collection of real-time data, enabling the analysis. But what is IoT in the context of landslide warnings? It includes the use of different sensors that are hopefully strategically placed in the landslide-prone areas, and the aim is to continuously collect data, and then to make this data available for analysis and interpretation. And these analyses can lead to identify patterns, anomalies, with the aim then to issue alerts and warnings. So we start, I think it's also here it's pretty clear that we need to have sensors online, real time, continuously providing data and making this data available, but then we need to interpret this data to do something and then to provide the results of our analysis. So this is what we are trying to do. And now I'm going to show you what is the structure that we are using and what is the structure we have used to build our model. So first of all, I want to start with a general structure of landslide early warning systems. And I was using, again, literature. Here I provide a small review of how different authors have schematized the main components of a landslide early warning system. On the left, you see what is provided in general for an early warning system, not related to landslide, in general, from the United Nations, disaster risk reduction. And then here you see different columns corresponding to different authors. Let me use the pointer here. Okay. Then, as you can see here, there are some components that are recurrent. And these ones are mostly monitoring, modeling, forecasting, warning, and response. So this is, from my point of view, these are the main 5 components if you want to build a reliable landslide early warning system. And this is the structure that we have, the framework that we have provided for an IoT-based local labs, with the aim of doing early warning for potential instability of rainfall-induced landslides where there are no evidences of active deformations. So we need to have a real-time monitoring in place of different hydrological variables, volumetric water content, for water pressure, suction, and also climate variables, rainfall, snow melting, temperature, so on. Then we need to have a model. So we need to use this monitoring data in some ways. Plus, we need to have input, soil hydraulic properties. We need to know them. We need to know vegetation properties, if any, and then soil parameters. Then we can build our hydrological model. We can do a calibration and validation. So basically, we can back calculate what we are monitoring to prove that our model is somehow reliable. And then we can have a slope stability analysis. So this type of modeling, I called it, using a buzzword that is popular nowadays, the digital twin. So we basically create a model that we somehow trust, that can represent what is happening in our real slope. Then we may use machine learning algorithms that can be trained out of the result of the numerical model. And then it can be used in the cloud in real time in a faster way. And then we need to forecast climate variables to use as input, and then to predict conditions leading to failure in the upcoming days. And then if there is any instability or any anomalies, then providing warnings that can be SMS, emails, whatever. And then the response we need, if a failure is imminent, then having emergency plan in place and action it and go with it. This is the general framework. Now, how we have used this framework in a practical way. And this is what I'm going to show you. This is our IoT structure. I need to also apologize because maybe some of these things may not look so nice. We are still in the process of producing the final figures for our paper. So this is our IoT structure. This is the monitoring. So we are monitoring different things, we're using sensors from different companies. And then this can be seen as our modeling part, where we use the monitoring data, we get the data, then we make the data available in what I have called here digital twin, which is our reliable model. We used this reliable model, numerical model, to train a machine learning algorithm. Then, so we have our model in place, and then we need to make forecasts. So we need to get climate variables forecasts from the meteorological office, in this case, the Norwegian Meteorological Office. So this goes into as an input into our digital twin. Then we make the prediction of different things, of hydrological variables and also factor of safety. And if the factor of safety and the hydrological variables exceed given thresholds, then we issue warnings. So we receive SMS and emails. This is the structure. This is the IoT structure that we are practically using. And this is how we have employed the main components of a lens that early warning. So monitoring, modeling, forecasting, and warning. As you can see here, NGI Live is the keys, the connection, is the link between all these parts. But what is NGI Live? And I'm going to take two more slides about that. So NGI Live, it's a data platform. We get wireless. We get data through wireless system, and then we have this Geo Hub that fetch data and store the data and makes the data available. And then we may use API to send to run applications, to run codes, and then to send and to plot the results in dashboards. This is the structure. This is what NGI does. What we are doing here specifically, we are getting the model inputs are fetched from data API, so we get that. And then the results are published through ingest API. So this is what we are doing, basically, as simple as that. Then the digital twin model is deployed as a cloud service using Azure functions, and then it's automatically triggered every day. So the data gets updated every day automatically. And then if the code changes, then the updates are deployed automatically in Git push. This is what we are doing. Now, let's see how we have done all these things in a practical application, in a case study. So this is the area, you see it on the right, in a very rare sunny day here in Norway. And you can see already that it's pretty steep on the right-hand side. I forgot to mention that you see pictures of people on the top right. It means that these are people that have helped in doing different things. So you will see different faces. This is not one person job. This is, we accomplished this topic and these tasks as a group, as a team. So you will see the faces of the people that have helped. This is important. I forgot to mention at the beginning. So this is the case study. As you can see, this is here is located the monitored slope, and here is a cultural heritage area. So no structural mitigation measures can be achieved on top of this slope. And here there is a double railway line. So at the toe, they have done something to stabilize the slope, but at the bottom, the slope is very steep, and it's threatening this railway line at the toe. So they decided to start monitoring the slope. This project started in 2016 with the monitoring. And then they have also performed CPTU investigations in the points that I'm showing you, ABC. These are the profiles, more or less, so you can see that up to 10 meters from the top, the material is different from 10 meters from the bottom, right? This is clear, you can see it clearly. The top part is in partially saturated conditions, and pressure plate tests have been carried out, and then we have used Bang-Newton equations to interpolate among points, among the pressure plate results. And then we had two different soils. The first one was going from 0 to 6 meters, and then the other one from 6 to 10, and then the third one, which is marine clay, from 10 to the bottom. And then on the right, you see the values used for the Bang-Newton equations, and also the parameters, the geotechnical parameters used for the constitutive model of NORWAY. This is the schematization of the slope. So we have sandy silt on top, clayey silt, and then marine clay. The water table is around 6 meters. It's fluctuating with seasons. And then you see all the monitoring sensors that are employed. On the right, you also see the slope that is heavily vegetated and quite very steep, around 40 degrees. So what are the sensors? We have 4 water pressure sensor piezometers, 4 different depths. These at the beginning were not in real time, that we have transformed them in real time recently. Then we have in green, the square are volumetric water content sensors from Delta Link. And then in red are volumetric water content and water potential sensors. And on top, we have installed also a small weather station that measures atmospheric pressure, precipitation, solar radiation, air temperature, and so on. So these are the measurements we have on the slope. And this is how it looks like. You can see the 2 different data loggers that we have, a solar panel to charge to give power to the data loggers, and because it's very important for our winter, it's very cold, and otherwise the batteries will run out of charge pretty fast. These are in details the details of the sensors we are using: Geotech PBT, a Delta Link soil moisture sensor. This is the Delta Link data logger, Teros 21 from the Matter group. Is in indirect estimation of suction. This is the data logger, volumetric water content, and a small weather station. Now here the challenge, our first challenge was, okay, these different data loggers, they send data to different clouds. So our first task was to get all this data and to put in one single dashboard. And this is what we have done using Grafana. I'll show you now how the data looks like. I think I need to remove the pointer here. Yeah, to run the video. Yeah. So we see the location, you see the railway line, you also see the structural mitigation measure that has been done at the top. You see the profile of the slope, precipitation. We also get information from a close meteorological station. Then our data, wind draws, wind speed, and other information. Then here we have for water pressure, and then soil temperature, volumetric water content, water potential, and so on. Everything is in real time. But as I was saying before, having data in real time, this is not an IoT. We needed to do something else. So we have done something more. We need to do something more. And on the left here, you can see the tabs that we are having. So map, a tab showing the map, slope cross section, the data from a close meteorological station, and then other variables. This is an example of how the data look like. We have pore water pressure on top, and then we have volumetric water content in the middle, and then soil temperature and precipitation. In this case, we have 4 years of data. Then how we have done the modeling. So we have seen the monitoring. Let's move to the modeling. How we have built our reliable model. We have used a commercial software, GeoStudio, very well known. We have coupled analysis with SIPW and slope, and we started back calculating 1 year period. And this is, we are considering precipitation and evapotranspiration up here, and then here just precipitation and evaporation. These are the layers. As I said, the first two are in partially saturated conditions. Then we started our analysis, our back calculation in a given time. This date was the 3rd of June. In this 3rd of June, you have a given volumetric profile in the soil. And you can see in blue the one that we were measuring at the 3rd of June when we started the first 1 year back calculation. Then, but the one that we were getting from the GeoStudio was, the standard one was this line, the dotted line here in black. And we called this kind of standard and this simulation as non-calibrated. But we wanted to match what we were monitoring from in terms of volumetric water content. So we tuned it a little bit. And then we had what we called a calibrated kind of start of the simulation, which is this kind of gray line and dots curve here. Then we had these 2 series of simulation. And what we have done for each of them, we have considered, in the first case, let me put the pointer again. We have considered only rainfall, the first simulation, then rainfall and climate variables, temperature, relative humidity, wind speed, so on and so on, and then also vegetation. And then the same we have done for the calibrated beginning of our analysis. So at the end, we had 6 simulations. And with CW, we can simulate soil vegetation atmosphere interaction. And the Penman-Monthly equation have been used for calculating evapotranspiration, and the root uptake, water uptake, was taken by Fredes et al. 2001. So now we wanted to check in this 1 year back calculation, which one of these 6 simulations was the best in back calculating our hydrological variables, the hydrological variables that we were monitoring. It means volumetric water content at 6 different depths and pore water pressure. Usually in literature, you would see something like that. So you see what you're measuring, the blue line, and then you see the different results of your models that you get. In this case, that we get considering different variables. Well, in this case, I would say it's pretty difficult to define which one is the best. So we decided to use tailored diagrams for the validation of our back analysis. How tailing stumps work. They work in this way. It's a radar. It looks like a radar. So you have correlations here going from 0 to 1. You have the normalized standard deviation 0, 1 is here, and then above 1. And then here you have the roof mean square differences. So basically, the closest are the dots. The dots are your simulation, our simulations in this case. The closest are to the dot here, to the reference point. The closer is our back calculation to what we are monitoring. So we have computed the correlation coefficient, the normalized standard deviation, and the root mean square differences, and the bias of the predicted, of the back calculated volumetric water content at 6 different depths and pore water pressure, and we have compared with the observed ones. This is the result of the validation using tailored diagrams. So at the end, briefly, we find out that with this preliminary calibration, using climate variables and vegetation was the best model to back calculate what we were monitoring. So here is the in situ condition, and here you can see that generally this CCLV is the one that agrees better than other simulation at almost all depths. You see it's here, you see it's here, and you see it here is the closest one, and so on. Then, to further improve the model and the back calculation or representing the in situ condition, we have performed a sensitivity analysis of the hydraulic conductivity, of the saturated horizontal hydraulic conductivity, so this value here, for the different 3 layers, and also the anisotropy of the hydraulic conductivity for the different 3 layers. So here are the results. Just to point you out some few things. In this case, if you increase the layer 1 permeability, you can see a faster response of the volumetric. You see volumetric water content here at 6 meter depth and the low water pressure here. So going from the simulation 0 to the simulation 1, you have a faster response of the volumetric water content. You can see it here, you can see it here as well. While if you increase the layer 2 hydraulic conductivity, you have a lower response. This is because 6 meters is at the edge between the two, at the boundary between the two layers, and it's where also you have the fluctuation of the water table, as you can see from the increasing volumetric water content measured, which is the blue line. And here is the pore water pressure, the measured pore water pressure. And the other continuous lines are the results of our model. Then we took the best model here, and we also changed the anisotropy ratio. And in this case, we can see that increasing the layer 1 anisotropy ratio also slower the response, as you can see here. Now, we defined that the best what were the best input parameters in terms of saturated hydraulic conductivity and the anisotropy ratio. We find out that this number 17 simulation was the best, and this is the final result. These are in the comparison between the observed volumetric water content at 6 different depths with the back calculated for 1 year of analysis. So in blue you see the monitored the observation, and in orange you see the model results. You can see that we are satisfied of what we are doing of our back calculation and at the end of our model. And this is the pore water pressure at 6 meter depth, where we have the fluctuation of the water table. Now we have in place a model that we somehow trust, and then we, on top of this CW analysis, we have calculated the factor of safety in time, and this is how it looks like. I need to remove the pointer to run. So basically, we were fixing the sliding surface, and we were considering and plotting the factor of safety in time for 1 year of analysis. Then what else we have done? We have done that, and we have our model that we trust, and we have back calculated all the variables for 1 year. Then we have done that using other databases. So at the end, we ended up using 5 years of analysis, 3 for the past scenarios, plus 2 future scenarios. So past scenarios, it means that we start in a day, and then we use as inputs all the climatic and vegetation variables, and then we run the simulation and we predict, and when we calculate the factor of safety. For the future scenarios, we have used the data from the Norwegian Meteorological Office. They are providing temperature and rainfall in the future on a daily basis. We understand that this can be not so much reliable, but they are doing that, plotting and considering that there's going to be an increase of up to 15% of more rainfall, and there's going to be an increase also of the temperatures. But for us, it doesn't really matter what day it's going to rain. For us, we wanted to enlarge our kind of database and then to have a larger data set to use to train our machine learning model. And this is what we did. So we used these different inputs of these 5 different scenarios together with the factor of safety. And then we divided this into different sets. We used different years for training, and we changed the year of the prediction. So what were the variables? The features were the 6 volumetric water content at the 6 different depths for water pressure, the rainfall, the temperature, and the leaf area index. And the target was the factor of safety. We tried different machine learning models, and we found out that the best one was random forest. So I'm going to show you what are the results. These have been performed by Minu. I guess many of you know her because she was working with Nelima at IIT Indoor. And these are the results for the 3 different sets. So we have that set 1 and set 3 were the best ones performing with a quite high R squared and pretty low value of the mean square error and root mean square error. But at the end, we decided to go for set 1 to use as model for making our predictions, even if we have a bit of higher uncertainties in the prediction. Here, what you see the predicted factor of safety of our machine learning trained model with, we call it true, but it's the factor of safety that it comes from the GeoStudio analysis and simulation. So in blue, you see the test, and in green, you see the validation. So even having a higher uncertainty, we have preferred using this set, because this set is okay, is a lower R squared, and also because it's going kind of horizontally here and that, we didn't like that so much. So we ended up picking up this set as trained machine learning for making the prediction in our. Now, just a very brief recap. I know I have just not so many minutes left, 5-6 minutes. What else is needed to make the prediction? So we have trained our model, our machine learning model. Feature are those ones, target is the factor of safety. Then we have the forecast meteorological data from the Norwegian Meteorological Office, rainfall, temperature, relative. But then if we want to make prediction of the factor of safety, let's say for the upcoming 3 days, this is what we are doing, then we cannot base our prediction on the past hydrological variables. So these are the variables that we need every day, right, to make the prediction for the upcoming 3 days. So we do have the climate variables from the Norwegian Meteorological Office. So what is missing at the moment is the hydrological variables. So we need to forecast them in the upcoming 3 days, and then to put those variables into our trained model in order to predict the factor of safety. How we have done that? Well, in this case, we have used pastas, not because I'm Italian, but just because we think it's a very nice tool to use. Is a new and open source Python package for the analysis of hydrogeological time series. And you can see the reference on top right, and at the bottom you can see a link to the website, which is very nice and explicative. So transfer function noise modeling tries to explain an observed time series, in this case, in our case, volumetric water content and water pressure, by one or more other observed time series. These transfer function noise models can be used to decompose these time series that we want to predict into the contribution of different hydrological stresses that causes the fluctuation of what we are targeting and what we want to predict. And then the contribution of stresses to the hydrological parameters that we are going to predict are computed through convolution and gamma distribution, and basically use it. I'm going to be very fast on this. If you want to know more, please go and check the paper and the website. This is what we have done. So we wanted to predict our hydrological variables, volumetric water content and water pressure. These are the variables we have used. So rainfall, temperature, solar radiation, snow depth, this area index, and relative humidity. And this is the result. So in black, you see what we were monitoring, and in blue, it's our back calculation, plus you have the 3 days forecast. This is what we are actually doing for the 6 different depths of the volumetric water content. The black is the observed data, and in red is what we are back calculating, plus the prediction at the very end. So this is for the volumetric water content and the water pressure. So the correlation coefficient is quite high in many cases, okay in others. So now, finally, how we are doing the things. Climate, here, let's imagine that this is the time of the run when we do the analysis. This is now. So we get all the past data. So we have from NGI, we get volumetric water content or water pressure. And then we have from the Norwegian Meteorological Office, precipitation, temperature, we calculate relative humidity. We put these things into pastas and we predict for the next 3 days the volumetric water content and pore water pressure. That these will be used in the pre-trained random forest model. Then for the future, we take the forecast of precipitation, relative humidity, and temperature. We use basically temperature, and we put into our trained model together with the volumetric water content and pore water pressure. And then we get out the factor of safety. I forgot to mention that in pastas, we also use solar radiation and leaf area index, but I have showed, I showed you before. And this is the way how we do the prediction of our factor of safety. This is the final result. Finally, we added a tab, which is called Digital Twin. And this is how it looks like now. And I'm going to conclude. So this is the area. This is the slope cross section. We have seen that before. This is our digital twin prediction. And this is the tab, the digital twin prediction for the upcoming. I've done this today, so this is for the upcoming 3 days. Nothing is changing so much. It's very cold now in Norway. It's mostly snowing, so it's not really happening anything. This is the standardized value of volumetric water content for water pressure, and this is the time series of the predicted factor of safety. And these graphs are the pore water pressure measured and predicted. And then further down, you have volumetric water content measured and predicted. Let's give a bit more a look, a bit more in detail of what we have. So this is what we plot, the normalized value of volumetric water content and pore water pressure. So basically it means that values close to 1 or that exceed 1, it means that we have never seen such a high value in the past. So that's the reason of this radar graph. We thought it was interesting. It gives you the idea of what are the variables with very high values. And then these are the actual values of continuous line, what we are monitoring on top volumetric water content, and dotted line, what we are predicting with the pastas module. And then here is the pore water pressure. So on top is the volumetric water content, at the bottom is the pore water pressure. And finally is the factor of safety for the upcoming 3 days. And well, nothing is changing, as you can see. So in the past weeks, the factor of safety time series has been more or less stable. We don't have not so much, no rainfall, just snow, cold, and not so much snow melting at the moment. Conclusion, takeaway, first part. We have proposed an approach to define an IoT-based digital twin, local labs, and the importance of using monitored data to back calculate the hydrological condition. So the importance to have a reliable model, digital twin, let's call it this way, that we trust, and the importance of having a calibration and validation. You can find this in way more details in the publication. Here is open access. You can scan the QR code and you can get it. The other takeaway, it will be published hopefully soon. The possibility to use volumetric water content, so hydrological variables plus climate variables to predict the factor of safety using machine learning. We have used machine learning because, as I said, we are running this automatically in real time, and it's faster and easier instead of using the software in the cloud. It would have given us a lot of issues. And then an automated procedures to compute the factor of safety, considering the forecasted climate variables up to 3 days. And then this concept can be easily adapted to other slopes. Of course, you need to rebuild the digital twin, but the concept and the structure, monitoring, modeling, and forecasting and warning can be applied. These are the references used in this presentation. Extra info, we are going, myself, Tina Peternel, Stefano Beriano, and also Nedima Satyam, Samuele Segoni, we are going to convene this session on Landsat early warning systems at the upcoming EGU. If you will be at EGU, please stop by, reach out, we can have a chat, a coffee, and we can discuss further on these topics. Another thing, I'm leading this working package 8 within the Landwehr community. Landwehr is an international community of experts in landslides early warnings. And this working group is about IoT-based monitoring and warning, case studies and pilots. If you want to join, please visit the website, subscribe. It's completely free. You will receive newsletters or scan the QR code. You will be updated about initiatives and workshops and so on. This was the last slide. Again, thank you very much for this opportunity. It was very nice for me to present our work and what we have done and achieved so far. If you have any questions, curiosity, please don't hesitate. Either you make them now or you reach out and with emails, and I will be very happy to talk to you. Thank you very much.
Thank you so much, Dr. Luca. It was an interesting lecture. So that's why I call you Dr. Luca, because anyway, so thank you so much. And so we'll have some, interaction with the participants. And so I was interested with your digital twin model, is it at what scale? I mean, you prepared the digital twin of the slope, right?
Sorry, say again. I couldn't.
Your digital twin forecasting model, right? I was interested to know more about that. I'll start with myself. So, is it like, you made the digital twin of the slope by considering the topo details and other drainage network, everything? Is that what I understood, right?
Yeah. This is what we have done for the slope, and this is what at the end we called it local landslide early warning system at a slope scale. So we did we were monitoring hydrological variables. We did the back calculation of it. Then we had this model in place. With the result of it, we trained a machine learning algorithm. We are taking forecasted weather variables, predicting factor of safety. Exactly what you said.
Sure. Yeah, that's very interesting and very novel aspect in disaster planning and forecasting.
Thanks.
So can I request the participants, if you have anything, to kindly you unmute yourself and you can post your question even in the chat box. So in spite of a public holiday, several people attended from India also, and we have people from BGS and other nations as well. So
Dr. Nilima, one question about the hydrological
how are you?
that back calculations. I'm fine. So my question is the back calculation just now mentioned, how it was being done. So I shall put in the chat box.
Yeah,
I shall put in the chat box.
Voice is not very clear to me, at least.
Maybe if I understood correctly, is how the back calculation has been performed. Is it something like that? Okay, I can say a few words about the back calculation. We were monitoring hydrological variables, volumetric water content, or water pressure. We wanted to build on the calibration process. What I'm reading now. Okay. So what we wanted to make sure is that our model, we wanted to use a model to kind of represent our in situ conditions, a reliable model that we trust.
You can check one time.
We use it GeoStudio, and we started with SEEP, and we had a monitored period. We used 1 year, and then we were using our, setting the model. And the important thing here was to define a starting period for our analysis. Once we defined the starting period, we decided at the end of in the summer season, where we thought, okay, maybe the summer season can be seen as a reset for the hydrological variables somehow. So we start from that. But then, of course, the calibration process and our first thought was, okay, but then volumetric water content will have a given profile due to the meteorological kind of situation you had in the previous days. So this was what we thought. So, and the standard profile of the GeoStudio SEEP was that one that I was showing you. So it was not exactly the same that we were monitoring in situ. So we decided to do this tuning, this calibration of the volumetric water content profile, just to start. We didn't want to start already with a mismatch between the two. And so this is what we did, and we find out that having a preliminary calibration was better at the end in kind of back calculation of the hydrological variables. I hope that the reply was answering your question.
Yeah. Thank you. It was clear. It was clear. Yeah.
Thanks. Other questions or curiosity?
Hi, I have one question.
Hi.
Hi, Luca. I'm Margherita from Pavia.
Hi, Margherita. Ciao.
Maybe I missed a thing, but why can't we get the 3 days forecast hydrological parameters only by using GeoStudio model, by inserting the rainfall forecast?
Yeah, the thing is that we were not using the GeoStudio in the cloud. This is the main thing. So the quick answer. So we are using a machine learning algorithm. In theory, we could do that practically with GeoStudio, right? So you are thinking that, okay, why you haven't done that? You can just put the forecasted weather variables, and then you get the volumetric water content and the water pressure. You could do that. It's a bit more tricky, not automatic to do. Plus, we are not having the software in the cloud. In the cloud, we are having the machine learning trained algorithm. This is the thing. So this is the reason why we needed to use something else to predict volumetric water content and water pressure. Was it clear, Margherita?
Okay, yeah, clear. Understand. Thank you, and thank you for the lecture.
Thanks. Welcome.
Dr. Luca, we have another question in the chat box regarding sensor.
Yeah, what is the sensor type used? Okay, we have. Maybe I can quickly show the slide again, because it's maybe easier to see what we have. Do you see the screen?
Not it.
Yeah, it's coming.
Yes.
Yeah, see it? Okay, but I need to go some very at the very beginning. Sorry for this quick going back. Okay, these are. Do you see clearly, or you see this kind of thing on? Yeah. Okay. So here are the sensor types that we have. Piezometers, these ones. Then we have volumetric water content sensors. These ones, the square, this one, we coupled it with the suction sensors, and we here.
Connection.
And then we have a meteorological station. And then we are also getting data from a nearby meteorological station, because we feel that the precipitation data from from us here is not the best. So we are getting another data set of precipitation from a close rain gauge station. These are the sensor types, and then these sensors they belong to different companies, as I have shown here. Do you have other questions about the sensors or some specific details you want to know, or it's clear? So mostly these are the sensors we are using: volumetric water content for water pressure, so piezometers, volumetric water content, and climate meteorological data. It's pretty simple to employ because it doesn't cost so much. If you think that a water content sensor is around maybe an average high-level one is around 200 euros, but now you can find volumetric water content for much lower price, and they are still equally good. I know that Margherita is working on that, and perhaps she will, or she has already published something, or you could double check that. And also a data logger, for instance, it costs around 600 euros. So it's not that expensive. You can employ these sensors with a very low budget, and you have your slope monitored. So another question. Okay, yeah, now I see it. How the prediction of future factor of safety or slope are verified? Very good question. We had discussions about that, and because of course we need to know if we are doing things correctly, right? So we will at a given point rerun some GeoStudio analysis in parallel to double check that what we are predicting is somehow correct. So this is what we are going to do. Yeah, but what we have done and test is that with a calibrated model, the other check we are doing is we are doing a check on the volumetric water content and for water pressure. So if we see, so we are plotting it, we can plot it internally with this pasta thing. If we see that we are going like far from what is the monitored value, then we know already that our predicted factor of safety will be off. So this is somehow already an indirect check we are doing, not directly on the factor of safety, but we are doing it indirectly on the variables we use it to predict the factor of safety. So volumetric water content and for water pressure. So we are somehow doing it already. And we will do also in parallel direct comparison of factor of safety. Very good question. Then there is another question: slopes having drainage channels, how this is taken into account. If I interpret the question here, maybe drainage channels, you mean, Govind, you can perhaps comment, you mean that inside the slope you may have like preferred way of water of infiltrating.
If I understand well, Govind sir, question is like, are you taking the streamlets, effect of streamlets, into your monitoring or in the slope stability analysis? Because when you have, drainage or the streamlets are there, so which are joining down the bottom, so maybe there may be some erosion and something like that, right?
Yeah, well, we are now considering the steepest part of this kind of 3D area. Of course, this is a 2D analysis. This is important to keep in mind. So we are representing and simulating the stability of a 2D of one section. which we think it was the most dangerous one, the steepest one. So we are not, this is what we are doing. We cannot at the moment consider like different drainage, external 3D drainage channels. But if in this case, we are talking of internal preferential way of water of moving, then in that case, we have improved our model considering this anisotropy of the hydraulic conductivity, right? It's somehow to take into account that water infiltrates, but then you may have different horizontal and vertical permeability that can distribute the water in different ways in the different layers. This is the other thing, and we have considered that with our sensitivity analysis, changing in both the saturated horizontal permeabilities of the different 3 layers, but most importantly, changing the anisotropy ratio of the 3 different layers. So playing with the anisotropy, with the ratio of the hydraulic conductivity in the vertical and horizontal direction. Yeah.
So thank you so much. So I request if the participants still have anything to interact, so they will contact you. And thank you so much, Dr. Luca. And we have Dr. A.P. Singh, who is a Honorary Secretary of Indian Geotechnical Society. So I'd like to request Dr. A.P. Singh to just say a few words about the IGS and other activities. Because
Thank you, Dr.
Technical Society is a very large, vibrant society with more than 5,500 members. Very strong representation in ISMG also.
Oh, thank you, Dr. Luca, for a very useful, valuable, and futuristic lecture, technical talk you have delivered. And really, IoT is going to have a very bright future in the on the global scenario, because this is the only tool which can be used for the remote monitoring. We cannot reach, but with this help, we can monitor 24/7. So thank you for delivering this lecture, and thanks to Professor Nilima for organizing this lecture series. You know, this is the 6th lecture of this lecture series on the field monitoring of geotechnics. And IGS is a very strong and large society. It is having almost 6,000 members, including life members, life fellow and all. And it has completed 75 glorious years. So it had a very glorious past and now going to have a very bright future in the coming time. And it has 53 local chapters, and each local chapter is in itself is a body, or like a mini IGS, you can say, throughout the India. Everywhere you go to a region, you will find a local chapter of IGS. So that is the visibility in India and globally also. And IGS is doing a lot of effort, and it gave the concept of Geotech Asia. That is the first, that is on the same line of Asian Regional Conference. So it gave the concept, and it won the first Geotech Asia conference to be organized in India and Goa in 2025. And this ISSMG has already given this international symposium on field monitoring of geomechanics. That will be organized in 2026 at IIT Indore under the leadership of Professor Nilima. So this way we are, it's moving very fast. And this year we had won, our young members have won 3 Bright Spark lectures also from ISSMG. And they have one of the Bright Spark lecture awardee is already is an ex-student of your Professor Nilima Satyam herself. So you can visualize how IGS is going to grow and how brightly it is going to organize the things. So hopefully you will come, you will be a part of this symposium in 2026, and
very nice.
The preparation of that. So thank you very much and welcome on behalf of Indian Geotech.
I think in next visit you should visit IIT Indore, Dr. Luca.
Yeah, as Professor Nilima Satyam was mentioning before, we have many ongoing at the moment projects with India. We have I'm leading one of them. It's called Klima. It's called Not Risk, basically. And I'm gonna make many travels in the upcoming years in India, and it will be a good occasion to just make a route and visiting IIT indoor, and hopefully we will collaborate in the future in proposals and other.
Yeah, sure. Anyway, Meenu is there, right?
And Meenu is there now as a connection.
India is already there in your institute.
Yeah.
Sure. Thank you so much, Dr.
Thank
Luca.
you.
It's such a nice to interact with you and such a great lecture. Hope to meet you again, host you again.
Yeah.
So thanks again. Okay. Thank you, everyone.
Thank you. Thank you.
Dr.
Thank
AP.
you very much. Really, very much to you, to also Kunal Gupta, that was behind this.
Kunal is a student of
Kunal
mine,
is there.
going to submit thesis very soon, who helped me in arranging this, coordinating all the things. Yeah. Thank you so much.
Thank you all the people attending in this National Day. Sorry, I had to postpone it in December. I was sick, but thank you very much. It was very nice.
But the recordings of all the lectures are going to be very useful in sharing the knowledge. So we are posting that in ISMG and IGS YouTube channels, official LinkedIn and YouTube channels. So thank you so much. I'll share the link with you as well. Thank you again.
Yeah.
Thank
you again.
Thank you, Luca.
Thanks for joining. Good day. Bye.
Bye.